Okay, so welcome back to this next video in which we are discussing cyclic groups and cyclic subgroups. Okay, so in the previous video what we discussed is cyclic groups. Okay, so we've seen the finite cyclic groups and we've seen the infinite cyclic group, which is the integers under addition. Okay, in this video what I want to move on to is the second topic. I want to move on to the topic of cyclic subgroups. Okay, so before we do that, let me just remind you of the concept of what a subgroup is, and then we'll see the special concept of what a cyclic subgroup is. Okay, so capital H is a subgroup of capital G, okay, written like so, capital H is less than capital G, means that capital H is a subset of capital G, first and foremost. Okay, so let me just show this. So capital G is some set, which I'll write like so, containing lots of symbols. Okay, and capital H is going to be some subset of the set of symbols that is capital G. So let me just color code this. Okay, so here we'll have capital H represented in green, and this subset of the set of symbols, which is capital G, is capital H. Okay, so I'll also color code up the set of capital G. So the entire set here is capital G. So capital H is first and foremost a subset of the symbols in the group capital G. Okay, and what we're going to do is we're going to take this set of symbols out and sit it on its own here. Okay, like so. Okay, and in order for this to be a subgroup, then what we have to do is we have to define a composition law on this set of symbols, and this composition law needs to obey the axioms of group theory. Okay, so if you take any subset of capital G, you can very easily define a composition law on it. Okay, what you can quite simply do is steal the composition law from capital G. Okay, so for instance, if you have two arbitrary little elements, little x and little y, which are elements of capital H, and you want to define what is little x composed with little y in your subset here, capital H, then quite simply what you can do is you can say, okay, little x and little y here, shown in green because they're in capital H, they are in capital G because capital H is fundamentally just a subset of capital G. That means that the answer to what x composed with y is equal to is in capital G. Okay, so there is an answer already defined in the composition law of capital G. Why don't we just nick that answer, basically? Okay, and indeed that's a very easy way to define a composition law on this set of symbols. Okay, just take all of the answers from capital G, steal the composition law, basically. Okay, so the fancy way of saying this is that we take the induced or inherited composition law from capital G, basically. And you can do that for any subset of capital G that you like. Okay, so any subset you could possibly dream up of capital G, you could form an induced composition law like so for it. Okay, now, in order for this subset here, with this composition law that we have stolen from capital G on it, to be considered a subgroup, however, this needs to be a group. Okay, so this set of symbols with this inherited composition law on it need to obey the axioms of group theory. Okay, then what we say is that capital H is indeed a subgroup of capital G. It's a group inside of capital G, basically, where if you were to pull it out of capital G and steal the composition law from capital G, or indeed you can also view it as restricting the composition law of capital G just down to the elements of capital H, then it forms a group on its own, basically. Okay, right, so let's just go through the axioms of group theory then to highlight what this composition law needs to obey in order for this subset to be a subgroup. Okay, so axiom number 1 of group theory is that the composition law needs to be closed. Okay, that says that whenever you compose two elements of the group together, you have to get another element of the group. Okay, so that means that all the entries in this composition table okay, they all need to be within our subset here, basically, within our subset capital H. Okay, now, that is not trivial one bit. Okay, what we know is because capital G is a group, then whenever we compose two elements, little x and little y together, that are in capital H, they're certainly in capital G, so you are assured to get an element that is in capital G simply because this is closed. However, you are not assured that when you compose these two elements together, you will necessarily end up with an element that's in capital G, but is specifically in the subset of capital G, which we're calling capital H. Okay, so it's not necessarily true that you'll end up not with an element that's outside of capital H, basically, but that would not be good. You want it to be within capital H. So basically, you need all of the answers here in this inherited composition law to be within capital H, basically. Okay, in order for closure to be true. Okay, right. Next, the second axiom of group theory is associativity. Now, associativity we get for free. Okay, if you took any subset you could possibly dream up of capital G and formed the inherited composition law on that subset, you would automatically get associativity being satisfied. Okay, the reason is that this little composition table we have here is a stolen part of the composition table on capital G. Okay, if it was not the case that this stolen portion of this composition table obeyed associativity, then it wouldn't obey associativity in the composition table of capital G. Basically, if it was the case that this composition table did not obey associativity, then it would be the case that the composition table in capital G didn't obey associativity, okay, and therefore that would contradict capital G being a group, basically. Okay, so it will always be the case that if capital G is a group, then whatever subset you take here and you form this stolen composition law, that stolen composition law will obey associativity. Okay, so you don't need to worry about associativity, basically. Axiom number 3 then is that we need to have an identity element in this inherited composition law. Okay, now that means that we're just going to need to make sure that in our subset here, one of the elements that we've actually included in that subset is the identity element from capital G. Okay, if we include the identity element from capital G in our subset, then we will have an identity element which will compose with any other element of this subset to give that other element back again, and that's true either way round that you compose them. Okay, so axiom number 3 just says that we need the identity element from capital G to be in capital H. And finally, axiom number 4, inverses. Okay, so if I have an arbitrary element, little a, which is an element of my subset, capital H, then basically I know that in capital G there will exist A inverse, okay? Because A is an element of capital G, and G is a group, so there must therefore exist the inverse element, okay, in capital G. What I'm saying now is that I also need that inverse element to be in capital H, basically. Okay, so if you have any element, little a, which is in H, you need to make sure that you've also included its inverse element from capital G in your subset, capital H. Okay, if it's going to be a subgroup. So you need to make sure that you've included these pairs of elements, i.e. an element and its inverse element. Okay, right, so that's what a subgroup then is. Okay, so now what we want to discuss is what is a cyclic subgroup. Okay, so this is a really nice, clever concept. Okay, so we want to be able to find subgroups of groups. Okay, cyclic subgroups are a very easy way to construct subgroups of groups, basically. Okay, so here's the idea. What you do is you generate a cyclic subgroup from an element of your group. Okay, so firstly what you need to do is we start off with our group capital G. So we're going to start off with some group that we want to find subgroups of. Okay, and we're going to construct some cyclic subgroups of this group. Okay, what you need to do is you need to take an element x, which is in G. Okay, and for it to be interesting, you need x to be not the identity, a non-identity element. Okay, so let's assume x isn't the identity element. Okay, what we can then construct is the cyclic subgroup generated by x, which is written like so. Okay, so we put triangular brackets around x, and you would read this as the cyclic subgroup generated by x. Okay, so I might just write that title down here. So you'd call this the cyclic subgroup, and you could just put of x, but more properly you put generated by x. So let me just show you what the definition of this is. Then I want to discuss why this is going to form a group. Okay, then I want to give you an example of it, and then I want to discuss that this is going to be isomorphic to cyclic groups, basically. Okay, right, so the cyclic subgroup generated by x. Okay, so the definition then of this cyclic subgroup generated by x then is, what we're going to do is we're going to create a subset that we want to be a subgroup. So the first thing that we might as well put in if we're trying to create a subgroup is we might as well put in the identity element, which I'll just call E. Okay, all subgroups have to contain the identity element, so if we're going to build a subgroup, we might as well just get that out of the way right now. Okay, so we'll start by putting in the identity element here, because that has to be there. Okay, then what we'll do is we'll put in this element x. Okay, so we've now got the element x there. Okay, now as soon as we've got this element x in there, we're going to need x composed with x, okay? Quite simply because if our subgroup has to be closed under composition, then x composed with x is also going to have to be in here, okay? Because otherwise it wouldn't be closed under composition. So what I'm now going to do is I'm going to put in x composed with x, which I'll denote x squared. So this is just x composed with itself, and that has to be there the instant x is there, okay? Then what I'm going to do is I'm going to have x composed with itself 3 times, because of course the instant we have x and x squared there, we can compose those two together to get x to the power of 3, x composed with itself 3 times, and basically I'll continue this argument on, and I'm going to put in all powers of x. So I'll put in x to the power of 4, x to the power of 5, and you can go on and on and on. Okay? What else are you going to need if this is going to be a subgroup? Okay, well we know it needs to contain the inverse element, so we're also going to need x inverse in here, so we'll stick x inverse in there. Okay, but once we've got x inverse in there, we're going to need x inverse composed with itself. Okay, so I'll now call that x to the power of -2, so this just means x inverse composed with itself twice, so x inverse composed with itself. Okay, so effectively it means x inverse squared. Okay, and we can go on, we can put x to the power of -3, which means x inverse composed with x inverse composed with x inverse, and then we'll have x to the power of -4, x inverse composed with x inverse composed with x inverse composed with x inverse. Okay, so we put in all powers of x, and we put in all powers of x inverse basically, and this is the subset that I am going to produce, and I claim that this is going to be a subgroup basically. Okay, and this is what is meant by the cyclic subgroup generated by x. So this is this basically. Okay, it's the identity element with all powers of x and all powers of x inverse. Okay, and it's quite helpful to think of the identity element actually as being x to the power of 0. Okay, because that then makes it very parallel here with x being raised to powers of the integers basically. Okay, and that will help us later on. Okay, right, so basically there's a problem here that you might be wondering about. Okay, this is an infinite set that we've created here. What looks to be an infinite set, what we've created here. Okay, and that's fine if the subgroup G that we are taking this cyclic subgroup of is an infinite group itself. Okay, but what if G is a finite group? How on earth can we have an infinite subset in this way of a finite group? Well, the answer there is that, of course, we won't have an infinite subset of a finite group. What will end up happening is not all of these different powers of x and x inverse will be distinct. Okay, so what will end up happening is loads of them will end up being the same answer, basically. Okay, and we'll end up adding the same thing into this set over and over again. Okay, which means that we might as well not bother adding it in at all. Okay, and that's how this can end up being a finite set. Okay, and we'll discuss that in more detail later on. Okay, but let's at the moment go for the simpler case, which is where all of these answers here are distinct. Okay, so that means our group, capital G here, is going to have to be infinite. So let's assume at the moment that we're working with an infinite group, and that we've selected some element x, which is a member of that infinite group. We've generated its cyclic subgroup, and all of these answers are different elements of the group, so we need to put in all of them. They're all different, okay? And I'll give you an example of that later on. Okay, so what we've got now then is an infinite cyclic subgroup. Okay, so we'll call this an infinite cyclic subgroup. So what I want to do is I want to firstly discuss why this infinite cyclic subgroup that I have here actually is a subgroup of capital G. Why does it obey the axioms of group theory? And then what I want to do is give you an example of a group G which I can generate an infinite cyclic subgroup of. Okay, and then I want to discuss the fact that these infinite cyclic subgroups are always isomorphic to the infinite cyclic group, i.e. the group of integers under addition. Okay, right, so let's start off with answering the question of why. Why does this form a subgroup, basically? So we need to make sure that it obeys closure, we need to make sure that the identity element is in there, and we need to make sure that it has inverse elements in there. Okay, so the first thing to actually do then is to answer closure. Okay, so we need to prove that if I take any two elements in this subset that I have here, and compose them together, that I end up with another element in that subset, basically. Okay, and in order to argue in favour of that, I need to tell you how you can actually compose two elements in this set together to get another element in that set. Okay, so let's think about how we can compose elements of this set together. So arbitrary elements of this set we can express as x to the power of a and x to the power of b. Okay, where a and b are integers, and this is where it becomes very, very helpful to relabel up the identity element here as x to the power of 0. Okay, then we can actually express all of these elements in this set here as x to the power of some integer, basically. If we make x here x to the power of 1 as well. Okay, so here I've got then two arbitrary elements of this set, xa and xb, and I want to ask, what is xa composed with xb? Well, hopefully you should intuitively be able to guess the answer here. It is going to be x, and then you're just going to add the powers, basically, a plus b. Okay, but I want to explain to you why that is the case. Okay, so let's split it up into three different cases. Let's split it up into the cases where firstly a and b are both positive integers, then we'll do the case where they're both negative integers, and then finally we'll do the most complicated case, which is when one is a positive integer and the other is a negative integer. Okay, so let's start off with case number 1 here, which is that a and b are both greater than 0. Okay, so they're both positive at the moment. Okay, right, so we want to prove that that's true when they're both positive. Okay, well hopefully that should be obvious. Okay, if they're both positive, then this is x to the power of some positive number, which just means x composed with itself a times. So this just means x composed with x, composed with dot dot dot, composed with x, a times, basically. Okay, if I now compose this with x to the power of b, b again is some positive integer, so again, let's just color code this in. Okay, so x to the power of a is here, here are the a little x's composed with one another. Now let's do x to the power of b here. So once again we can write x to the power of b as just x composed with dot 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 composed with x, this time b times. Okay, so let's colour code that in orange. And then if we're going to compose these two together, then what we'll end up with is x composed with x composed with x composed with x. How many times now? Well, it's a plus b times, and that's why this is just x to the power of a plus b. So we've proven that that's the case when both a and b are positive integers, basically. Okay, now let's think about the case where both a and b are negative integers. Well, it's exactly the same argument, except that now we think of x inverse instead of x. Okay, so case 2 now, let's think about when a and b are both less than 0, so they're both negative now. Okay, so if we have x to the power of a, and we're taking it composed with x to the power of b, then what does x to the power of a now mean when a is some negative integer? Well, that now means x inverse composed with itself a number of times. So this means x inverse composed with x inverse composed with dot 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 composed with x inverse a number of times, basically. Okay, so once again I'll colour code this in. So this is yellow here. Okay, now x to the power of b, again, b is now a negative integer, so this is going to mean x to the power of -1 composed with itself b times again. So it's x inverse composed with x inverse composed with dot 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 composed with x inverse b number of times. Okay, and when we compose those two things together, what we're now going to get is, oh, and I'm sorry, I've made a little bit of a mistake here. I should have put negative a, negative b there. Or maybe, it's probably best if I then put negative a, negative b here. Let me just redo this. Okay, so let's say that a and b are actually positive integers here, but that we have negative there to make the powers of x negative. Okay, I think that's the best way of doing this. So get rid of those negatives there. Okay, right, that's correct then now. So we have x to the power of -a composed with x to the power of -b, where a and b are both just positive integers, okay, which means that these powers are now negative integers. Then that means x inverse composed with itself a number of times, and this one means x inverse composed with itself a b number of times. I apologise for that. Okay, right. So then when we compose them together, what of course do we end up with? We end up with x inverse composed with itself a plus b times. So this will be x to the power of -a plus b, basically. Okay, which is just x to the power of -a plus -b. So effectively we have just added the powers there, basically. Okay, I think that's the best way of showing that. Okay, so it's exactly the same argument as we had here, except that we've swapped x for x inverse, basically. Okay, right, so that's case 2. Now what we have to do is case 3, where the two powers of x that we're going to have, one will be positive and one might be negative, basically. Okay, well, I think the best way of getting the intuition for that is just to do an example. Okay, so let's just think about x to the power of 4 composed with x to the power of -3. Okay, what does this actually mean? Well, x to the power of 4 just means x composed with x composed with x composed with x 4 times, and then x to the power of -3 means x to the power of -1, x inverse, composed with itself 3 times, like so. Okay, and then what's going to happen is the x's are going to cancel with the x inverses. Okay, so you'll cancel this x with this x inverse. Okay, you'll cancel this x with this x inverse. Okay, and then you'll cancel this x with this x inverse, and then what are you left with now? You're left with 1x left over. Okay, so that's just x to the power of 1. Okay, so hopefully you can see that what we have done is we've just added 4 to -3, basically. Okay, and this argument would generalize more. Okay, so what we then do is say, okay, let's go a bit more general. Let's have x to the power of a composed with x to the power of negative b, where once again a and b are just positive integers, we're assuming, and therefore the power here is negative. Okay, then what would these two combine together be? Well, again, you'd write this out as x composed with itself a times, and then this one as x inverse composed with itself b times, and you'd cancel as many x's and x inverses as you have, and then you'd see what's left over. And again, that's just the same as adding a to b, basically. Okay, a plus negative b would be the answer here. So we'd have x to the power of a minus b, which is really just a plus negative b, i.e. you just add the two powers here. Okay, right, so that then is why when you compose any two elements together in this cyclic subgroup here, this infinite cyclic subgroup that we are assuming we have, you're just adding the powers. Okay, and when, for instance, you take something like x to the power of 3 composed with x to the power of negative 3, then of course you have an equal number of x's and x inverses, so you'll completely cancel down and you'll just end up with the identity, but we've agreed that we will call the identity x to the power of 0, which is very helpful because then our rule still works. Okay, so that's why it works so nicely. Okay, so now then, it should be very obvious that this is going to be closed under composition, because whenever you add two powers of x, you end up with another power of x, okay, and all the powers of x are captured in this set, basically. We've got all of them, okay, so that is then why it's going to be closed under composition. Okay, so we've handled closure. This is going to be closed, okay? You're not going to get an element that's outside of the cyclic subgroup. Okay, next what we want to prove is that we've got the identity element. Well, there it is. Okay, so we do have an identity, okay? And finally, we want to prove that we have inverses. Well, again, hopefully that should be pretty clear. Okay, if I have some element x to the power of a, where a is some positive integer, then I can just look at the element x to the power of negative a. Okay, so this one is x composed with itself a times, this one is x inverse composed with itself a times. Clearly they will annihilate each other and reduce it back to the identity. Okay, so every element here does have an inverse, basically. We have inverse pairs included in this subset here. Okay, so it does form a subgroup then. Okay, so what I want to now do is give you an example of an infinite group where we can take an infinite cyclic subgroup, and then I want to argue that all infinite cyclic subgroups, like so, of any group you can take, okay, any group you can think of, and for any element little x that you can use to generate it, are isomorphic to the infinite cyclic group, which is the group of integers under addition. And hopefully, now that we've seen the way that you compose any two elements in here together, you might be able to understand why that's going to be. Okay, right, so let's now have a look at an example then of an infinite cyclic subgroup. Okay, right, so we're going to actually go back to the group of integers under addition, and I apologise because we are using the group of integers under addition for an awful lot, but it's a nice, easy one that everyone's got a good intuitive understanding of. Okay, so we're going to use as our group that we're going to take infinite cyclic subgroups of, the group of integers under addition, okay, which we can write like so. Okay, here's the set, which is the set of all integers, and then we've got our composition law like so. So that's often a common notation people use for groups. Okay, they put the set here, and then they'll put a comma, and then they'll put the composition law here. So this is the group of integers under addition. Okay, so what I'm going to do is generate a cyclic subgroup that's going to be infinite within this infinite group. Okay, so quite simply, I'm going to generate the cyclic subgroup from 2, okay, as a nice example. So 2 is certainly an integer, it's a non-identity integer. Now, I should just say that when you choose to use the identity as the little x. The reason I said I wanted little x to be a non-identity element was not that you can't do the definition of a cyclic subgroup for the identity. You can, it's just you end up with a very boring subgroup. You end up with the trivial subgroup which just contains the identity, because the identity, all the powers of the identity element are just the identity back again. The inverse of the identity is just the identity back again. So basically all of these elements just end up being identity, and therefore the only thing that you end up with in this set is just the identity, so you end up with that trivial subgroup which is just the identity on its own, which is indeed a subgroup of all groups. But it's not a particularly interesting one. Okay, so that's why I said we wanted a non-identity element. So 2 is a non-identity element, so it should generate us an interesting cyclic subgroup. And indeed it is going to generate us an infinite cyclic subgroup. Okay, so let's create the set then. Okay, so we start off by putting the identity element in. Now in the case of the group of integers under addition, the identity element is 0, so we'll start off by putting in 0, then we'll put in x, which is 2, and then we want to put in all powers of x. Now don't get confused here. When I say powers of x, remember I mean x composed with itself by a certain number of times. Okay, I do not mean actually do powers, okay? I mean compose it with itself a certain number of times. Okay, so when I say I want 2 composed with itself, basically, I'm going to add 2 to 2. So 2 plus 2, 2 composed with itself, is then going to equal 4. Okay, then if I want 2 composed with itself 3 times, okay, I'll have 2 plus 2 plus 2. Okay, so we'll then end up with 6. Then I'll do 2 to the power of 4 effectively, but remember we're not meaning powers as you would think in classical algebra. We're meaning powers in terms of composition, which is addition. So this is 2 plus 2 plus 2 plus 2, which will then be 8. Okay, and you can go on, so you'll get all multiples of 2 basically, so you'll get 10 and 12 and 14, and it will go on and on and on. Okay, so these are all of these powers of x basically. You just have to remember that composition here is just addition. Okay, right, now what we want, the other elements we want is x inverse and all powers of x inverse, so let's put those in. So we'll then put in negative 2, which is x inverse. Okay, and then we're going to put in all powers of negative 2, so we want negative 2 plus negative 2. Okay, that will be negative 4. We want negative 2 plus negative 2 plus negative 2, that will be negative 6. We want negative 2 plus negative 2 plus negative 2 plus negative 2, that will be negative 8, and you'll go on. So you'll get negative 10, negative 12, negative 14, and it will go on as well. Okay, so here now we have generated this cyclic subgroup, which is an infinite cyclic subgroup, because hopefully you can then realize that as you go on, the elements that you continue to get will never ever be the same as elements that you've already got. You'll always get new elements. Okay, and the set that you're actually building here is just all integer multiples of 2. It's the set 2z, and in previous video where we discussed subgroups, we showed that 2z is in fact a subgroup of the group of integers under addition, and we can see here that actually it's the cyclic subgroup generated by the element 2. Okay, right, so there's an example of an infinite cyclic subgroup of a group basically. Okay, right, what I now want to do is go back to more abstract settings, so forget this nice concrete example, we're going to go back to the more abstract group, G, okay, and we'll go back to the more abstract cyclic subgroup, the cyclic subgroup generated by some element x, which is an element of G. And I want to prove that these infinite cyclic subgroups are always isomorphic to the infinite cyclic group, which is the group of integers under addition. Okay, now going back to our example here, that means that this infinite cyclic subgroup, which is 2z, is isomorphic to the infinite cyclic group, which is the group of integers under addition. Okay, and that's what we showed in the previous video where we talked about subgroups. Okay, we showed that this subgroup 2z, the integer multiples of 2 basically, was indeed actually isomorphic to the group that we'd taken it as a subgroup of, okay, which is the group of integers under addition. Okay, what we're now going to prove is that that's true for the more general infinite cyclic subgroup. Okay, right, so to show that the infinite cyclic subgroup is isomorphic to the infinite cyclic group, what I need to do is find you an isomorphism. Okay, so I need to find you a mapping phi from my infinite cyclic group here, x, onto my group of integers under addition basically. Okay, and this needs to be a bijective map, okay, so it needs to be 1 to 1 and onto, okay, and it also needs to obey that property of isomorphisms, that phi of, and I shouldn't use the symbol x, so I'll use another symbol, little a composed with little b is equal to phi of a composed with phi of b. Okay, so we need to find such an isomorphism basically, and then we can prove that the infinite cyclic subgroup is always going to be isomorphic to the infinite cyclic group. Okay, right. So let me just show you then this isomorphism, and hopefully it should be pretty obvious. Okay, so the isomorphism then is going to take any power of x. Okay, so let's say x to the power of little n, and it's just going to take it onto the integer little n. So let's just remember or write down here what this infinite cyclic subgroup actually consisted of. Remember, it consisted of all of these integral powers of x. You had x to the 0, which was the identity. You had x to the 1, x to the 2, x to the 3, etc. on like so. And then you had all the negative powers as well, x to the negative 1, x to the negative 2, x to the negative 3 here. Okay, so that was our infinite cyclic subgroup. What I am now saying is I'll take any element which I can call x to the power of little n here, where little n is some integer. Okay, and I'm just going to map it onto little n basically. Okay, so that's a pretty obvious map to choose basically. Okay, it's certainly a bijective map. Every element here is going to go onto an element in the integers. It's going to be 1 to 1 because every integer is going to get one of these being mapped onto it. Okay, and only one, so it's not going to end up being many to 1. Okay, it's also going to be onto because all of the integers are represented here basically. We have x to the power of any integer, therefore any integer here will have some power of x being mapped onto it basically. So it is a bijective map basically, so it satisfies that criterion that it is a nice relabeling map. Now we need to show that the composition law that we have in here is the same effectively under this remapping as the composition law in the group of integers under addition. Okay, right. So remember the composition here on this side where we've got phi of a composed with b, that means the composition in our infinite cyclic subgroup here, which we do call abstract composition here. Okay, whereas composition on this side, this means composition in this group here. Now, what do we usually call composition in the group of integers under addition? Well, we call that addition. So I might just replace this with phi of a plus phi of b here. Okay, right. So let's now try and prove that this property is true. So what we need to do is take two arbitrary elements, little a and little b, which are elements of my infinite cyclic subgroup generated by x here. Okay, now I've said that arbitrary elements of this infinite cyclic subgroup generated by x here can be represented as powers of x. So let's say little a will call now x to the power of little n, and little b now will call x to the power of m, where n and m are some integers basically. Okay, so little a and little b were just arbitrary elements of this group. Arbitrary elements of this group can be written as powers of x. Okay, that's all I've done now. I've said we're going to have some arbitrary element of this group, and we can write that as a power of x, and another arbitrary element of this group, which we can also write as a power of x. Okay, right. So what I now want to prove then is that phi of x to the power of n composed with x to the power of n is equal to phi of x to the power of n plus phi of x to the power of m, and that needs to be true for all little n and little m are elements of the integers, so that it's going to be true for any arbitrary elements of this cyclic subgroup generated by x, basically. Okay, well, let's just apply what the actual mapping is. Okay, so on this side then, we need to firstly compose these two together, okay, and then we need to act the map on it. Okay, act the map on what the answer to these two composed together is. So what are these two composed together in this group here? Okay, well, of course, it is just x to the power of n plus m. That's what I showed you over here, basically, that if you want to compose two powers of x together, you just add the two powers. Okay, so if we compose them together in the infinite cyclic subgroup generated by x, we get x to the power of m plus n. We're then taking phi of x to the power of m plus m, which will just take these to n plus m, basically. So the answer to the left-hand side is just n plus m, basically. Okay, now let's have a look at the answer on this side. So phi of x to the power of n, what's written up there, is just going to be n. Okay, and phi of x to the power of m is just m. And then we've got n plus m, and this means those two compose together in the group of integers under addition, but of course that's exactly the same as n plus m that we had over here. Okay, so that's why these two groups are isomorphic, because we have now established an isomorphism between them. Okay, and that's true for an arbitrary little n and an arbitrary little m are elements of the integers. So it proves basically that the composition laws, when we relabel the composition law of the infinite cyclic subgroup generated by x, it does actually turn it into the composition law of the group of integers under addition. Okay, and hopefully that should be pretty obvious from the way in which we know we compose any two elements here, just by adding together the powers that the elements are raised to, basically. Okay, and that's just like the way that we compose integers together. Indeed, we are using the group of integers under addition to understand this infinite cyclic subgroup, basically. Okay, right, so we'll call it there for this video. In the next video, we'll discuss finite cyclic subgroups rather than infinite cyclic subgroups. Okay, so we'll discuss what happens when not all of these different powers of x and x inverse are distinct elements.